Good afternoon, dears. I am Dr. N.M. Ganesan, Associate Professor, Department of Physics, Erode Engineering College. In this valuable session, I like to share some information about semiconductors. Before to see this particular topic called semiconductor, the topic that we are going to cover are conductors, semiconductors, properties of semiconductors, explanations on the basis of band theory, types of semiconductor, preparations of different types of semiconductor, variations of Fermi levels, and identifications of semiconductors. Dear students, before to see the semiconductor directly, we shall see something about conductors. In conductors, the conductivity is defined by the number of free electrons available in it, whereas in the semiconductor, the conductivity is not only decided by the electrons but also holes. For understanding purpose, the electronic configurations for ion is given for your well-beings. In this electronic configuration, you might know there are two free electrons. These free electrons are randomly moving inside the conductor. These are responsible for conductivity in the conductors. As a ion atom contribute only 2 electrons for conductivity, the conductivity depends only on this number of free electrons. Its conductivity cannot be increased further. In the case of semiconductor, the electronic configuration is shown. It has 4 valence electron. Here, the conductivity is not decided only by these free electrons, but also the number of electrons in the conduction band as well as number of holes in the valency band. In the conductor, as I said already, the conductivity totally depends upon number of free electrons, whereas in the semiconductor, the conductivity is the sum of conductivity of electron and the conductivity of holes. Some important properties are for your knowledge. The resistivity of a semiconductor is less than an insulator but higher than a conductor. The resistivity means opposition force given by the material to the flow of electron. It is very high for insulator, very small for conductor, whereas for semiconductor it is in between the conductor and the insulator. The conductors have electrical resistivity on the order of 10 to the power of minus 18 to 10 power minus 4 ohm centimeter, whereas insulator have electrical resistivity on the order of 10 power 8 to 10 power 18 ohm centimeter. It is very high, so we cannot give that much of electron to move from valency band to conduction band in the case of insulator. That is why a wood, a rubber, a plastic are always act as an insulator. Semiconductor have an electrical resistivity value between those of conductor and insulators, that is 10 power minus 4 to 10 power 8 ohm centimeter. The conducting property of a semiconductor changes when a suitable metallic impurity is added to it, which is a very important and notable point regarding the semiconductor. That means the added impurity alone decides the conductivity and type of conductivity also. The graph shows one of the major property of a semiconductor named as negative temperature coefficient. In the case of conductor, as temperatures increases, the resistivity also increases. So as temperatures increases, resistivity increases. As a result, conductivity decreases. This is because as temperatures increases, the lattice vibration also increases, which does not allow the electron to move from one end to another end easily. This is the main reason for the existence of resistance in proportion with the temperature. But in the case of semiconductor, as temperatures increases, the number of charge carrier produced increases in proportion with the temperature. That is why in a semiconductor, as temperatures increases, resistivity decreases, which leads increase in conductivity. The conductor, semiconductor and insulator can be explained with the help of energy band diagrams. In the first case, for conductor, the valency band and conduction band are overlap with each other. You might know very well that the outermost electrons are called valence electrons. These electrons together form a bond called valency band. The empty band over the valency band is called conduction band. Usually at low temperature, usually in conductor, both the conduction band and valency bands are overlapped each other. So whatever it may be the temperature, it may be the lowest temperatures minus 273 degrees Celsius or above room temperatures, electron can easily move from valency band to conduction band. So we can surely say that at any temperature, the conductor will not lose its conducting property. The main reason is that free electrons are always available in the conduction band as it is being overlapped with the valency band. If suppose we saw the energy band diagram for insulator, the band gap value between the valency band and conduction band is huge. It is nearly equal to 2 electron volt. So to move an electron from valency band to conduction band, we must give at least 2 electron volt to a electron. It is an impossible task. So in the case of insulator, at whatever may be the temperature, electron cannot gain more than 2 electron volt and goes to the conduction band. That is why insulator never act as a conductor at whatever may be the temperature. But in the case of semiconductor, the band gap value is in between the conductor, that is above the conductor and below the insulator. Suppose if we raise the temperatures just above the room temperature or in the room temperature, that temperature is sufficient to move the electron from valency band to conduction band. So the semiconductor will act as a conductor. If suppose reduce the temperature to minus scale, in this case the temperature is not sufficient to move the electron from valency band to conduction band. By seeing the energy band diagram, we can understand the conducting behavior of a semiconductor, conductor and insulator. Further, the semiconductor can be classified into intrinsic semiconductor and eccentric semiconductor. Intrinsic semiconductor is nothing but a full form of elements like silicon and germanium, whereas eccentric semiconductor are exist by the additions of impurities with the intrinsic semiconductor, and the type of additions of impurity further split the eccentric semiconductor into two types, named as n-type semiconductor and p-type semiconductor. They are formed by adding impurity. If we add pentavalent element phosphorus arsenic, we will get n-type semiconductor. If we add trivalent impurities like aluminum and indium, that will lead p-type semiconductors. We shall see about this type of semiconductor in detail in the next chapter. For your understanding purpose, we can define that semiconductors that are chemically pure, in other words free from impurities, are termed as intrinsic semiconductor. The number of holes and electrons is therefore determined by the properties of material itself instead of impurities. These are the some intrinsic semiconductor behavior. In the intrinsic semiconductor, always number of electron in conduction band is equal to number of holes in the valency band. In a nutshell, we can say that intrinsic semiconductor is a pure form of semiconductor. The number of electron and a hole is determined by the properties of semiconductor, and they are always equal to each other. Silicon and germanium are usually called as elemental semiconductor, while silicon and germanium are doped with aluminum, indium, phosphorus, arsenic and other elements to form the eccentric semiconductors. As I said already, phosphorus and arsenic are pentavalent impurities, aluminum and indium are trivalent impurities. So they will lead two types of semiconductors. So one is n-type semiconductor, another one is p-type semiconductor. For our understanding purpose, and the bond structures of an intrinsic semiconductor is shown in this slide. Here the silicon have 14 valency. Among them, 4 valence electrons are available in the outermost bond. These 4 electrons are used to form the covalent bond by sharing the electron with the adjacent silicon atoms. The electronic configurations of silicon is shown, as well as the covalent bond structures always also shown in these slides. In order to get an eccentric semiconductor, the intrinsic semiconductor must be doped with impurity atoms, either phosphorus, arsenic, antimony, aluminum or indium. Here the atomic configurations of phosphorus is shown in figure. Here the valence electron is 5. If you add these phosphorus with the silicon, you will get the structures like this, bonding structures. As we saw in the previous slide, that phosphorus have 5 electron, valence electron. Among the 5 electrons, 4 electrons are involving to form the covalent bond with the adjacent silicon atoms. It is clear in this picture. Each phosphorus atom donates 1 electron, excess electron, for conductivity. That is also marked as green in color. This leads n-type semiconductors because this donor atom ready to do this type of atom ready to donate an electron. That is why it is called a donor atom. In the second picture, the bonding structures of aluminum with silicon is shown. As I said earlier, the aluminum and the indium having 3 electrons in the outermost orbit, so they contribute only 3 electrons to form 4 covalent bond with the silicon atom. If you watch this diagram, aluminum contribute 3 electrons to form 3 covalent bond. It is a completed. In the 4th covalent bond, silicon alone contribute 1 electron, whereas aluminum cannot contribute electron, so that place become hole, and that hole has always a tendency to attract electron from the adjacent. That is why these types of atoms are called acceptor atom, because they are ready to accept the electron. Because of these dopings, particularly n-type material and p-type material, they form an additional energy level. So if suppose we add the pentavalent impurities, they will form a donor energy level very nearer to the conduction band. These donor atoms are ready to donate those excess electrons even at the low temperature. Whereas the additions of phosphorus and indium are ready to accept the electrons, so they form a energy level called acceptor energy level very close to the valency band. Even at low temperatures, electron cannot jump from valency band to conduction band. At that time, the small jump or small migrations of electron from valency band to the acceptor energy level will be accepted by this acceptor level. As a result, hole and electrons are available. Further, that once we formed them n-type semiconductor or p-type semiconductor, and the variations of Fermi level is very important with respect to the temperatures. For easier, I took only for n-type semiconductor. As temperatures increases, the Fermi level which are lying in between the conduction band and donor level make a transition to the intrinsic Fermi level. The downward transition might be stopped by adding the sufficient number of donor atom in the donor atom. If we do it, we will get a more number of donor atom and donor energy levels nearer to the conduction band. As a result, whatever it may be the temperatures, all the thermal energy is absorbed by the donor atom and donate the electrons from donor level to conduction band itself. This is possible by adding more number of donor atoms, that is 10 power 28 atom per meter cube, that will prevent the downward transitions of Fermi level towards the extrinsic energy level. This is true in the case of n-type semiconductor, whereas in the p-type semiconductor, upward transition will take place. The upward transition can be stopped by adding more number of trivalent impurities. If you do it, means those trivalent atoms accept the electron from valency band. By this way, we can prevent either the downward transition in the case of n-type semiconductor or upward transition in the p-type semiconductor can be controlled by adding the impurity up to the level 10 to the power of 8 atom per meter cube. 10 to the power of 28 atom per meter cube. After developing a semiconductor, by seeing the material, we cannot predict whether it belongs to N-type semiconductor or P-type semiconductor. This can be tested only with the help of Hall effect arrangements. In this case, current is allowed to pass through the given semiconductor and the magnetic field is applied perpendicular to the current direction. And if you do it means electron will make a migration from top layer to the lower layer. So on the top layer will have negative charges, bottom layer will have, as electron make a transition from top layer to bottom layer will have negative charges, on the top layer will have only positive charges. As the charges are separated, a voltage will be developed. This is called a Hall voltage. That type of effect is called Hall effect. By knowing the polarities, we can decide whether the given material is N-type semiconductor or P-type semiconductor. In a N-type semiconductor, electrons are migrating to the downward directions of a semiconductor, whereas in the case of P-type semiconductor, holes are making a downward transition. So in N-type semiconductor, as the electrons are moving a downward transition, the bottom layer of the slab will have the negative potential and the top layer of the slab will have positive potential. By using the multimeter, we can tell whether the given material is N-type or P-type. In the case of P-type semiconductor, all the holes will make a downward transition. So the bottom of the slab will have positive potential and the top of the slab will have negative potential. By this way, we can easily identify whether the given conductor is belongs to N-type semiconductor or P-type semiconductor.